This video should be fairly short. It's about something called telescoping series. To understand how to do telescoping series, we have to remember partial fraction decomposition. So if you remember how to do partial fractions, great. I effectively want you to use the process of partial fraction decomposition to rewrite this rational expression in this form. Right? So go ahead and try that on your own. Make sure you remember how to do it. If you don't remember how to do it, then watch through it here. The way we do it is we factor the denominator. Right? We recognize the denominator factors as x plus 1 times x plus 3. Then we say that 10 over x squared plus 4x plus 3 can be written as something over x plus 1 plus something else over x plus 3. Next, we multiply the entire problem, both sides, through by x squared plus 4x plus 3. When I do that, the left side becomes 10, the right side becomes a times x plus 3 plus b times x plus 1. Then our next step was sort of making a convenient substitution. First I'll say let's let x be negative 3. When x is negative 3, 10 will be equal to, this first part's going to turn into 0. So I'll end up with, well, when I put in negative 3 here, I'll get negative 2b. Basically means that b has to be negative 5. Then I'll let x be negative 1. When I'll do that, I'll get 10 equals 2a, plus 0. In short, a is going to end up being 5. Right? So at the end of this thing, my conclusion is that I can write 10 over x squared plus 4x plus 3 as 5 over x plus 1 minus 5 over x plus 3. That is how partial fraction decomposition works. I'm now going to use that with a series. Alright, so using the partial fraction decomposition from the previous example, compute the following infinite summation. So I'm now asking you what this infinite sum is. And you should be just blown away, because it means I want you to evaluate this expression from 0 all the way up to infinity, and then add them all up. Right, and I want you to tell me what that sum is. And you may think that's kind of difficult, so maybe we could do partial sums. Maybe we could just write out what these infinite terms are, and then start doing partial sums, and see if we can find out what they approach. That's horrible, right? Because this can be broken into partial fractions, because partial fraction decomposition works, this might be a telescoping series. So what I'm going to do is I'm going to rewrite this series, and I'm going to use my partial fraction decomposition instead. It was 5 over x plus 1 minus 5 over x plus 3. Right? So there it is. And now what I'm going to do is I'm going to start writing out the terms of the series. Let's first put in 0. When I put in 0 first, I end up with 5 over 1 minus 5 over 3. That's the first term. Plus, now I'll put in 1. That would be 5 over 2 minus 5 over, I'm putting in 1. So 5 over 2 minus 5 over 4. Plus, now let's put in 2. This will be 5 over 3 minus 5 over 5. Right. Just for good measure, let's do a couple more of them. Next up would be 5 over 4 minus 5 over 6. At this point, you probably see that there's a pattern that's happening here. 5 over 5 minus 5 over 7. And this is going to continue on forever. What's neat about this thing is that when I add these things up, look at what happens, right? I have a negative 5/3 added with a positive 5/3. Those will add up to 0. I have a negative 5/4 and a positive 5/4. Those will add up to 0. I have a negative 5/5 and a positive 5/5. Those will add up to 0. Right? The idea is that as I go infinitely far along, nothing will ever subtract off the 5 over 1 or the 5 over 2. Now what's interesting is that it's also true that nothing will subtract off the 5/6 and the 5/7. Well, that's actually not true. Eventually something will subtract the 5/6 and the 5/7. But as I keep going on and on and on and on and on, what's happening to these two terms? those two terms are both getting smaller and smaller and smaller. I mean, I only went up to the 5th term here. If I went up to like the 1,000th term, I went up to the 1,000th term, sorry, I would have something like 5 over 1,000 and 5 over 1,001. Those terms are getting very, very close to 0. It turns out that in this telescoping series, all that really seems to matter is the 5 over 1 and the 5 over 2. Right? When I add those two things together, I end up with, let's see here, that would be 10 over 2, 15 over 2. That is the sum of this series. Because everything else will either subtract off or tend towards 0, all that's really going to matter are those first terms, which means the infinite series is 15 over 2. The reason this thing is called a telescoping series, in my mind, is sort of imagine one of those like old school telescopes or like a spyglass where there's like things that nest inside of each other, and this is the eyepiece on the end. The idea is we have an infinite series, but you could sort of like collapse the whole thing down to just being the initial part. Turns out all that's going to matter is that initial part. So that's why it's called a telescoping series. So, in summary, I'm only going to do one example. In summary, a telescoping series is a very specific type of series that results from a particular type of partial fraction decomposition. It's a little bit rare that it happens. Actually, it's rare that you can actually find what the sum of a series is. Often, we're just going to be happy to say, hey, look, it converges. I don't know what it converges to, but it converges. With a telescoping series, if you recognize, hey, I could use partial fractions on that, you should try it, and you should see if it's telescoping. If it does, it means you're done.